In our previous video, we made a multi-layer perceptron neural network for classification. We can also do this vanilla neural network for regression. And so we can, instead of predicting whether something falls into one category or not, we can predict the outcome. So what we're going to do is take the data set we use to look at linear regression and create a multi-layer perceptron neural network to see how accurate it is compared to that regression model. Because really a multi-layer perceptron is only one step up from a regression model. All it's doing is adding some hidden layers. So basically a regression model is just input and output. We're adding a couple layers in between, but when we do our multi-layer perceptron model, we are assuming that we have fully connected neurons. Whereas if we get to more advanced versions, CNN, RNN type of neural networks, then you don't have fully connected neurons. Okay, we need to choose some nonlinear activation functions for our model. And so we talked in previous videos about that activation function. There are different types of activation functions. Many of the activation functions are used for converting to output. In our classification model, we use the sigmoidal function because we were doing binary classification. If we were doing multi-label classification, we would use softmax for our last layer. In this case, we are going to be doing regression, linear regression. Okay, so we're going to have a more linear activation function for the output. So this is the final layer in the process. If you are doing more sentiment, positive, negative, then you use a tan function. And for many of the layers in the middle, because we are assuming fully connected neurons, we are going to use this rectified linear unit, which is a variant of binary and linear functions combined. So we need to make decisions about the activation functions that we're going to use. And we do use different activation functions depending on where we are in the model. So the first couple of hidden layers have different activation functions than in the end when we're trying to convert all that information into our final output. Okay. We need to decide on the size of the data set, the proportion of training and testing, the type of network we're going to be using, the number of hidden layers that we're going to have. So if we go back to these visuals here, we have our inputs. Each one of these we have 3 layers in this example. With the multi-layer perceptron, we're doing, a minimum 3 layers. You can get to be more complicated when you do CNNs with images. You might have lots of layers depending on how complex the images are. But in our basic vanilla neural network, we'll just go with about 3 layers. All right. We are going to need to choose, when it comes to our neural network, how many repetitions, how many epochs we're going to have as we go through the network and then go back through it again. Those are called epochs. And then we're also going to need to decide what we're going to use for a model optimizer. We have SGD, RMS prop, and ATOM. These are different forms. What they're trying to do is keep the model from getting stuck in local minimums, but to find the point at which the error is actually globally the smallest. What combination of weights and assumptions get us there? And so there are different approaches. There are 3, and if your model isn't working particularly well, it's not stable. So every time you run it, you get very different results. Then try changing to a different optimization. But what they are doing is they're all looking at the gradient descent, which is why SGD is, but GD in it is gradient descent. So when we're looking at the error, and in this case, mean squared error, how do we get that mean square error as low as possible? What combination of inputs gets us there? We will then need to also choose some metrics for assessing our model, and that's going to depend on what type of model we have. Accuracy, precision, recall, area under the curve are all going to be for the binary classification. Categorical cross entropy is for when we have multiple labels, which means that in this case with our regression model where the output is going to be interval or ratio, we have the choice of mean square error, root mean square error, mean absolute percent error, or R squared. In our forecasting models, in our regression models, we often looked at the coefficient of determination, how much of the variability in the data, how much of the variability in the output variable is explained by the variability in the input variables, and we're looking for a higher R squared. With our forecasting models, 80% was the ideal. As you start to get higher, you run the risk of overfitting and not having a good R squared, essentially, for the new data that's not in the model when it was created. So we can look at mean square error and R squared in this particular scenario. So let's go in. We are working in the Artificial Neural Network workbook, which you can find at drstephpowers.github.io/BIA. And you'll find us here under Chapter 10, Prescriptive Analytics, Neural Networks. And here you can open this. It'll open into GitHub, which will then give you a button to open in Google Colab. So we're running this in Google Colab. And in this case, what we're going to be doing is using a data set here that is the New York Stock Exchange data. This is not a good application of this particular data set. This data set has a lot of multicollinearity. There's a lot of correlation between variables. We're actually not even treating it appropriately because the data set actually has the same company in multiple lines, and we're treating them as if they were independent. So we're using this data set simply to show linear regression, but given the actual data's setup, this is not the data set for that. So just a heads up on that. You can find that data set is called fundamentals.csv in the GitHub when you click inside. In order to access it, dump it into your Google Drive. Then once you've saved a copy of your workbook, connect your workbook to your Google Drive so that you can pull in your data sets here. So we're mounting the Google Drive so that I can import the CSV files. So as soon as that's done, we'll load her in. In terms of doing this analysis, I guess I'm not running pandas as PD at the moment. Let's load that in. Well, we're going to need, of course, in addition to pandas as PD, because we need that to load in our CSV file, we also are going to need our train test split from our sklearn model selection. That's going to allow us to separate the data into a test group and a train group. And because neural networks are highly sensitive to the numbers that are in those input variables, we need to standardize. So anytime you have any kind of interval ratio data in your neural network, you need to standardize. So we're going to use standard scalar for that. And then we're going to need our pieces for our neural network. Now, MLP regression, you could do it in sklearn. It's kind of black box. It does it all for you. It treats it very much like just a simple regression model, puts a couple layers in there, and it doesn't have a lot of choices for you. We want you to learn about how neural networks work and all the different decisions you can make and play with those. And so we're going to do even these very vanilla neural networks in TensorFlow with Keras. So you will need to import the Keras model that is sequential. That is for that feed forward types of neural networks. We only go one direction through the neural network. And then we need our optimizers. Here we're loading in Atom, SGD, or RMS prop. We'll go with Atom to start. That's kind of the most popular optimizer, but you can try the other ones if you're seeing that every time you run it, it changes quite a bit. If it's not very stable, again, it can be getting stuck when it's looking at that gradient descent. We're going to use the metric R squared, so we need to make sure we import our metrics that we are using. And then we're going to be using dense layers in these very vanilla neural networks. We'll add more complicated layers in more complicated neural networks, but here we just need dense. So let's load her in. Now, in this particular data set, if we look at the whole thing, there's actually a lot of columns. We don't need a whole lot of these. We're actually just going to pick a couple. And so we're just going to pick a couple of the ratios that you use to assess the viability of the organization: current ratio, gross margin, after-tax return on equity, cash ratio, and current ratio. I looked at that and thought, oh my goodness, I'm doing the same variable twice. No, we have different variables here. So these are as we pull out of the financial statements, because this is the income statement and the balance sheets are what this data set is of 4 different companies at different times. And we're going to pretend, so we're just ignoring here, that these are the same companies, and we'll just say, okay, here's the earnings per share. Can we predict this earnings per share? So again, we're really bastardizing this data set and not using it as it should be. So we're assuming a lot of independence that doesn't exist, which is why it's not a greatly performing data set. Okay, so what we're going to do is we're going to create a subset of this table. We're going to call it stock 2 because we call the first one stock. And we're just going to take the earnings per share, which is what we're trying to predict, cash ratio, after tax, gross margin, current ratio. We're going to make a subset, and then we're going to drop the NAs because there are other NAs in this data set, and we don't want to drop those and lose a bunch of data for variables that we don't care about. So reduce it down first, then drop the NAs. Then we split into our test and training data. So we're going to use cash ratio, after tax, gross margin, and current ratio, those variables as our training data. As our predictor variables, we're trying to predict earnings per share. We don't stratify here because there's lots of different earnings per share, unlike classification models where you have to make sure there's some in the test and the train. With interval ratio data, you don't do that. We're doing 80% in the train and 20% in the test. We are going to standardize, so we're going to have it use standard scalar to transform the training data and the testing data, so make sure you run that. With our multi-layer perceptron neural network, it is feed forward, so the model here is sequential. And now we need to add our layers here. Okay, and with our layers, we have the output space. And the output space, again, as we talked about in our previous one, should be to the power of the number of variables that we have here. Here we have 4, so 4 to the power of 2, to the power of 3, to the power of 4, kind of helping determine how many you should have. So here we'll start at 16 and then we'll go down. You can, of course, play with those a bit. When we're doing our multi-level perceptrons, then that output space is going to get smaller and smaller until we get to our final predicted number. And so the output, the last hidden layer here is going to be an output space of 1. Okay. Now we need an input shape, and our input shape is going to be 4. We have 4 variables. Our kernel initializer in all of this is normal. We're assuming linear regression, so we're going to have that normal component there. And then we need to specify our activation. And so we have this activation here, our ReLU, in the middle hidden layers. All right, so let's add those layers. And then we need an optimizer. We'll go with Atom. We need a way to measure the loss function. So how are you going to measure the error? And here we're going to use mean square error, so MSE. And then we're going to have it report the R² score. Okay. And so when we run this, we decide on how many epochs we're going to have, how many times we're going to go through. The more epochs, the longer it takes, and the more computing capacity it takes. These are very simple neural networks. We can do about 200 or 500 epochs, okay, in Google Colab. When you have more complicated neural networks with a lot more layers, a lot more complicated data, a lot more epochs, than Google Colab, at least your free version, can't handle it. So just a warning. All right, so let's run through this. We can see here our loss function and our R². And so again, because we are using a data set that's not actually in the shape of what we're creating a model for, you can see that R² is very low. And what we can see here is mean squared error alone doesn't tell us anything. We simply use it to compare models. Lower is better. And we want to see if the model is improving. So we're using back propagation, right? It goes through the model and then it is going to adjust those weights and hidden layers and is then going to run through it again. So what we should see as we run these R squareds is we should see improvement. Now in 200, there's not a whole lot of improvement here. We can run it. I think I might have separated out. Yeah, separated here. We can run it instead with 500 epic. We'll look first at the 200 and then we'll do a comparison with 500. So once we have run this, we want to assess the model. Well, we can't use the accuracy and precision recall as we were using before, false positives, false negatives, because it is a interval or ratio data. What we do want to look at is what is happening with our loss function. So we can pull, we named this, let's go back. So we named where we fit the model, we named that results. So whatever you name this here, this is where we're going to go down and we're going to do results, the name of that. And we want is the history. We want the history of the loss because as it's running through those 200 epics, it is printing out a loss function, or it's providing a loss function here. So what we want to do is actually just graph that. So we're going to look at the number of epics on the horizontal. That was our 200. Our Y label is going to be our MSE here. We can change this. I just have it as error, as generic, but it is technically MSE because that's what we told it to do for the loss function. And we can label that and graph it. And so what we should see is that we should see that loss function getting lower and lower. That is us getting to that global minimum MSE, that global minimum measurement error, and not getting stuck in those little local minimums as we were talking about with that gradient descent. So there should be descent and it should get smaller and smaller. And then it's going to kind of start to plateau and it's not going to be able to find any kind of combination of weights and bias and layers that is going to get it any lower than possible. Well, here we get lower and lower. We can't quite tell here if this has leveled off. So that's why we would go and run more epics and see if we get any improvement. Before we do that though, let's just run this here so we can see. Here we can see our R squared for the training data. And again, it's always going to have a higher R squared or metric for the training data because you built the model with that data. And then what we really care about is the test R squared, and you can see that it's very terrible. Not even 1% of the variability has been explained by our model here. And this is the new data that wasn't used in the model. So we really need to improve this by getting this number higher. Well, one thing we could do is have more epics so that it's going back through the model more times and then adjusting all of those hidden layers and how much weight and bias we have here to get a better model. So let's try running this here with more epics to see if we can get it up higher. So gotta wait a minute while it runs 500 of them, see if we can do any better. If you are doing our assignment or any of our practice where you're comparing a regression model and a multi-layer perceptron regression model, so you're adding those layers in, then with that training and test data, you can choose a random state, give it a number, random state equals, and that will then allow you to use the same data set in your neural network and in your regression model to do your comparison so that you're actually using the same testing and training. And so it is a greater comparison. So we have run here and notice that the R squareds are now sitting around 12% compared to where we were in the past. So I named it the same, which means I'm going to just rerun this piece here. We were at less than 0.005, and this one was at 0.04. So let's see if we do better. So notice we went from 0.04 to 12, and we went from 0.005 to 12. And notice these are a lot closer to each other as well, which is good. We have a much more usable model here. So just by changing the number of times it's gone through, we've already substantially improved this model. Once you have a model that is usable, and again, this one's never going to get super high because we're misusing the data, then what you can do is then you can predict. And so here, if we do y predict, then what we are creating here, y pred, is notice that these are earnings per share. And so we could put in new data here for the different financial ratios and get then an estimate of the earnings per share for new data. And so this one doesn't require any conversion like that the MLP classifier did. It comes out exactly as an earnings per share number. Right? So take a look, see if you can improve the model. There is another data set here. This one is the Auto MPG data set. And this one is looking at predicting miles per gallon. This comes from this one. You can just get it directly from the university that it has hosting the data. So we don't have to download it, save it to your Google Drive since we're just testing and playing here. And when you do this, you load it in as a URL. Here are the column names. And then what we're doing is it is a CSV, so we need to make sure we represent the components of that file. So this will give you a data set here that we have a column for miles per gallon. So can you create a multi-layer perceptron model that predicts the number of miles per gallon using horsepower, weight of the vehicle, acceleration, displacement? So using some of these variables here, how accurate of a model can you create? So give that a try and see if you can create a multi-layer perceptron neural network for regression type data.